What if every choice you've ever made, every fork in the road, every fleeting thought didn't just fade into the past, but splintered off into entirely new realities? Picture a universe where your decision to grab coffee this morning spun off one timeline, while skipping it created another, each unfolding in parallel, invisible to the other. This isn't just science fiction, it's one of the most startling possibilities quantum mechanics dares to suggest. Time, as we experience it, feels straightforward, a river flowing in one direction. But beneath the surface of our everyday lives, the rules of reality might be far stranger, far more fluid than we ever imagined. Quantum mechanics doesn't just challenge our understanding of particles and waves, it shatters our very perception of time itself. Think of the universe not as a single thread, but as an endlessly branching tapestry, with every possible outcome woven into its fabric. Some physicists argue that the moment you observe a quantum event, the universe splits, creating alternate versions of reality where every potential outcome plays out. One version of you might be reading this on a couch, while another, just a quantum flicker away, is hiking a mountain trail or boarding a spaceship. The implications are dizzying. If these timelines exist, where do they lead? Could they intersect or even collide? Over the next 30 theories, we're diving deep into the heart of this cosmic mystery. From the haunting elegance of the many worlds interpretation to the radical ideas of time as a hologram or a loop, we'll explore how science is grappling with the true nature of existence. Some theories suggest timelines ripple like waves, others that they're stacked like pages in a book waiting to be flipped, and the most mind-bending part. These aren't just thought experiments. Cutting-edge experiments in labs around the world are hunting for clues, teasing apart the fabric of reality to find out if we're truly alone in this version of the cosmos, or if infinite versions of us are out there, living out every path not taken. So buckle up. By the end of this journey, you might never look at time or yourself the same way again. Let's start with the theory that kicked open the door to infinite realities, the many worlds interpretation. In 1957, a young physicist named Hugh Everett proposed something radical. What if the universe doesn't choose between possibilities but embraces them all? Imagine you're flipping a coin. In our everyday experience, it lands as either heads or tails, but Everett's math suggested something wild. The moment the coin flips, reality splits. In one universe, it's heads, in another, it's tails. Both outcomes happen, just in separate, branching timelines. This idea wasn't just about coins or cats, though yes, we'll get to Schrödinger's famous feline in a moment. It was about rewiring how we see existence itself. Quantum mechanics had long puzzled over how particles seem to exist in multiple states until observed, a phenomenon called superposition. Traditional thinking said observation collapses this fuzzy cloud of possibilities into one outcome, but Everett's genius was to ask, what if nothing collapses? What if every possible outcome simply plays out somewhere? Take Schrödinger's cat, the thought experiment where a feline in a box is both alive and dead until someone checks. The many worlds interpretation flips the script. There's no spooky collapse, just two real parallel worlds. In one, the cat purrs, in another, it doesn't. Both are equally true, unfolding like strands in an infinite cosmic braid. Critics argue this is extravagantly wasteful. Why would the universe need countless copies of itself? But supporters fire back. Isn't it more elegant than magical collapse? No hidden mechanisms, no observers granting reality special privileges, just pure, unfiltered possibility. And here's where it gets even stranger. If every quantum flicker spawns new timelines, then somewhere out there, a version of you chose every path you didn't. The job you turned down, taken, the train you missed, caught, the words you left unspoken, said. Yet for all its grandeur, the many worlds interpretation raises thorny questions. Why can't we perceive these other worlds? How do probabilities work if everything happens? And if infinite versions of us exist, does any single choice truly matter? Everett's answer was subtle. These branches aren't fantasies, they're as real as the air in your lungs. They just diverge, like shadows cast by the same light, forever separate but born from the same source. Laboratories are now testing these ideas with quantum computers and entangled particles, hunting for echoes of alternate timelines. Could we ever detect them? Maybe, but for now, the many worlds interpretation stands as a breathtaking reminder. Reality might not just be stranger than we imagine, it might be stranger than we can imagine. And this is just the first theory. If the many worlds interpretation is correct, then reality isn't just branching, it's exploding into a kaleidoscope of possibilities, each split spawning trillions more in an endless cascade. Think of it like a mirror reflecting another mirror, creating infinite corridors of existence where every choice, every chance event spins off new worlds. This isn't just a multiverse, it's a fractal mosaic with patterns repeating at every scale. A single quantum decision, like whether a photon goes left or right, could ripple outward, altering the fate of galaxies in some distant branch. But here's where it gets personal. If every quantum event creates new timelines, then somewhere out there, another you made every possible choice you didn't. A version who said yes to that risky job offer, or who boarded a different train and met a soulmate you'll never know. These aren't hypothetical doppelgangers, they're as real as you are, just separated by the thin veil of quantum divergence. Philosophers wrestle with the implications. If infinite versions of you exist, does free will even mean anything? Or are we all just passengers riding the waves of probability, each path predetermined by the universe's unshakable math? Science isn't leaving this to speculation. In labs today, quantum computers are probing the edges of this theory. Take interference experiments where particles seem to remember paths they didn't take, as if ghostly echoes of alternate timelines are nudging them. In 2019, researchers at Google's Quantum Lab observed behavior in their Sycamore processor that hinted at parallel realities briefly overlapping, like shadows passing through one another. These aren't proof of the multiverse yet, but they're tantalizing clues that reality might be far more interconnected than we thought. Critics argue this mosaic multiverse is untestable, a cosmic sleight of hand. But supporters counter, isn't it stranger to assume our single timeline is special? After all, nature loves patterns from snowflakes to spiral galaxies. Why would reality stop at just one universe when it could paint with every color of possibility? The debate rages on, but one thing's certain. If the mosaic is real, then every moment is a crossroads, and every version of you is out there somewhere, living a life that's both unimaginably alien and hauntingly familiar. But what if branching timelines aren't created by conscious observation at all? What if the universe isn't waiting for us to look before it makes up its mind? This is where decoherence theory enters the picture, a radical twist on how quantum probabilities crystallize into the single reality we experience. Picture a detective at a crime scene, not by choice, but because every footstep, every breath leaves traces that give them away. In the quantum world, it's not a conscious observer that forces particles to pick a state, it's the environment itself, constantly leaving fingerprints on reality. Take the famous double-slit experiment where particles like electrons are fired at a barrier with two openings. When unobserved, they behave like waves, creating an interference pattern, as if each particle passes through both slits simultaneously. But the moment you try to measure which slit it goes through, the interference vanishes. The particle chooses a path. Traditional interpretation said this was the observer's doing, but decoherence flips that idea. It's not about human awareness, it's about information leaking. Every particle is entangled with its surroundings. Air molecules, stray photons, even the vibrations of atoms in the lab table. All these interactions nudge the quantum system like ripples disturbing a pond. Over time, this environmental noise destroys the delicate superposition, forcing the particle to settle into one state. Think of it like trying to whisper a secret in a crowded room. The moment your words interact with the chaos around you, their original meaning scatters beyond recovery. The universe isn't making a conscious choice, it's drowning in data. This leads to a startling conclusion. The collapse of quantum states isn't a special event triggered by minds. It's inevitable, happening constantly as particles bump into the world. When Schrödinger's cat is in the box, it's not just the scientist's gaze that seals its fate, it's the air molecules hitting the vial, the Geiger counter's atoms vibrating. The environment records the outcome long before a human ever lifts the lid. Decoherence also offers a way to reconcile the many worlds interpretation with our single timeline experience. Imagine those branching universes don't split cleanly but blur at the edges, like colors bleeding on wet paper. As decoherence spreads, the branches become permanently separate, their histories no longer able to interfere with each other. We don't perceive other timelines because we're trapped in one thread of this unraveling tapestry, deaf to the echoes of alternate paths. Critics argue this still doesn't explain why our timeline feels uniquely real, why we don't experience the ghost versions of events. But supporters counter, maybe we do. Every time a quantum system decoheres, we're simply riding one ripple in an ocean of possibilities, blind to the waves that didn't touch us. Experiments with ultra-cold atoms and isolated quantum systems support this. The less a particle interacts with its environment, the longer it stays in superposition, as if resisting the universe's demand to pick a side. So next time you face a choice whether to turn left or right, speak or stay silent, remember, the universe isn't waiting for you to decide. It's already splintering with or without you, as countless versions of this moment scatter into the quantum static. The real mystery isn't why we see one timeline, but whether we're the ones choosing or just along for the ride. Now imagine a version of you that never dies, not because of some miracle, but because the laws of quantum physics might demand it. This is the spine-tingling premise of quantum immortality, a theory that suggests consciousness isn't just along for the ride in these branching timelines, but actively steers toward realities where it survives. Picture a grim thought experiment. You're sitting in front of a so-called quantum suicide device, a gun rigged to a radioactive atom. If the atom decays, the gun fires. If it doesn't, nothing happens. In any single universe, the odds seem bleak. Eventually, the atom will decay and the gun will fire. But here's the twist: from your perspective, you'd never experience that outcome. In the timelines where the gun fires, you're gone. But in the ones where it doesn't, you're still here, unaware of the other versions where luck ran out. This isn't just macabre speculation, it's a direct consequence of applying the many worlds interpretation to consciousness. Physicist Max Tegmark, among others, has wrestled with the idea that our subjective experience might be tethered to the timelines where we persist, like a river carving the path of least resistance. Every near-miss accident, every brush with danger, could be a moment where countless versions of you perish, while you, the version reading this right now, only remember surviving. It's as if reality itself has a selection bias, filtering out the timelines where your story ends. Critics, of course, pounce on the slippery metaphysics here. If consciousness can hop timelines, why don't we remember the close calls? Why wouldn't we notice sudden jumps like glitches in a simulation? Tegmark counters that memory is tied to the physical brain, and in the branches where you live, there's no record of the deaths you didn't experience. It's not that you're lucky, it's that the other outcomes, by definition, aren't part of your continuity, but the implications stretch far beyond parlor games. Quantum immortality forces us to ask, what does it even mean to be you? If countless versions of your consciousness are constantly splintering, is there a true self, or just an endless chorus of near-identical voices singing slightly different tunes? And if survival isn't just chance but a feature of reality's structure, Does that mean death is an illusion or just someone else's reality? Experiments can't exactly test this without, well, volunteers willing to gamble with quantum guns. But the theory lingers because it touches something primal, our fear of oblivion and the tantalizing possibility that the universe might conspire to keep us here in some form against all odds. Whether it's science or philosophy, one thing's clear: the line between living and dying might be far blurrier than we ever dared to believe. Chaos theory tells us a butterfly's wings might stir a hurricane halfway across the globe, but what if that butterfly were a quantum particle, and those ripples didn't just alter weather patterns but reality itself? This is where the mundane meets the cosmic, where the tiniest quantum hiccup doesn't merely change outcomes, it spawns entirely new universes. Picture the newborn cosmos, a seething ocean of vacuum fluctuations where particles wink in and out of existence, borrowing energy from nothingness. In our familiar world, these quantum jitters average out, vanishing without a trace. But in the first instance after the Big Bang, when the universe was smaller than an atom, a single fluctuation could have been the pebble that started an avalanche, cascading into wildly different versions of spacetime. Consider vacuum decay, a scenario where a quantum bubble of true vacuum forms, rewriting the fundamental laws of physics as it expands at light speed. In one universe, that bubble never sparked. In another, it swallowed existence before the first stars formed. These aren't just hypotheticals, they're potential forks in the quantum road, where the universe's initial conditions were so delicate that a fluctuation one way meant gravity held galaxies together, while a flicker the other way left matter too scattered to ever coalesce. The butterfly effect doesn't just apply to storms, it might be the hidden architect of the multiverse. Lab experiments hint at how this could work. Ultra-precise measurements of quantum systems show that even shielding particles from outside noise can't stop their inherent randomness. Like trying to balance a pencil on its tip, the slightest uncertainty sends reality tumbling down one path or another. Cosmologists suggest that during cosmic inflation, the universe's explosive early growth quantum fluctuations stretched to macroscopic scales, seeding the galaxies we see today. But if inflation didn't end uniformly everywhere, patches of spacetime might have cooled into wildly different physical constants, creating a quilt of universes where gravity is stronger, light slower, or atoms impossible. The implications are staggering. Every quantum event in those first moments wasn't just a roll of the dice, it was a roll that created new dice, new tables, even new casinos. Somewhere out there, a version of the universe exists where every impossible combination of physics plays out. Critics argue this renders science pointless. If everything happens, how do we test anything? But proponents counter that we're not just passive observers. The fact we're here in a universe stable enough for life means we're part of a self-selecting subset where the quantum dice landed just right. So the next time you swat away a mosquito or miss a step, remember, on the quantum scale, those mundane moments might be the echoes of cosmic divergences, alternate realities where the insect's flight path or your stumble sent ripples through time, spawning universes where history unfolded just slightly or unimaginably differently. The butterfly effect isn't confined to weather. It might be the universe's oldest storyteller, whispering infinite variations of existence into being with every quantum shudder. We think of time as an unstoppable river flowing forward from past to future, but quantum entanglement might be twisting that river into knots. Imagine two particles so deeply linked that changing one instantly affects the other, no matter how far apart they are. Now suppose that connection doesn't just defy space, it bends time itself. Recent experiments suggest entangled particles might not just communicate faster than light, they could be influencing each other backwards in time, as if the future is reaching into the past to rewrite the rules. Take the famous delayed choice experiment, where physicists entangled photons and then made decisions about how to measure them after the particles had already started their journey. Somehow, the photons seem to know what measurement would happen later, adjusting their behavior accordingly. It's as if time's arrow isn't fixed, it's more like a two-way street with quantum effects blurring the line between cause and effect. This isn't just about particles being quirky. If entanglement can reach backwards, then the universe might not have a single, tidy timeline where events unfold in orderly sequence. Instead, it could be a tangled web where past and future are in constant conversation, negotiating reality moment by moment. Some theorists argue this could explain why time flows at all. Entropy, the tendency of systems to become more disordered, gives us our everyday sense of time's direction. Eggs break but don't unbreak, ice melts but doesn't refreeze on its own. But what if entropy itself emerges from quantum entanglement? Picture the early universe as a pristine, unentangled state. As particles interacted, they became knotted together, and those knots created an irreversible flow of information. A cosmic ledger where events stack up in one direction because entanglement keeps recording them. The arrow of time, then, might just be the universe getting increasingly tangled in its own quantum threads. Critics point out that retroactive influence sounds like magic, violating everything we know about causality. But supporters fire back. Maybe causality itself is a macroscopic illusion, a shorthand for processes that look linear to us but are fundamentally symmetrical at the quantum level. After all, if a particle doesn't choose its state until observed, why couldn't that observation include future events? Labs are pushing this further with quantum switches that alter past configurations based on future decisions, essentially building devices where cause and effect can swap places. The results are preliminary, but they hint at a truth even Einstein might have balked at. Time isn't the rigid scaffold we thought. It's more like a dance with entanglement calling the steps. So the next time you lament a choice you can't take back, remember, on some quantum level, the universe might not distinguish between before and after. The past could still be in flux, nudged by futures we haven't yet seen. And if that's true, then now isn't just a point on a line. It's a shimmering moment where all possible times are still in play. What if everything we experience, every star, every thought, every moment of time, is just a shadow cast by information we can't see? This is the wild promise of the holographic universe theory, where our three-dimensional reality might be nothing more than a projection from a two-dimensional surface at the edge of the cosmos. Theorized by physicist Leonard Susskind in the 1990s, this idea didn't start as a hypothesis about time. It began as a solution to a black hole paradox. When matter falls into a black hole, its information shouldn't vanish, but where does it go? Susskind's answer was radical: the data isn't destroyed. It's smeared across the black hole's event horizon like a cosmic hard drive, with every particle's quantum state encoded in swirling patterns on its surface. Now imagine scaling this up to the entire universe. If a black hole's interior can be described entirely by information on its boundary, why couldn't the same be true for reality itself? Picture the universe as a vast, glowing sphere with the past, present, and future written like lines of code on its outer shell. Our lived experience, the depth of space, the flow of time, would just be a hologram, a three-dimensional illusion projected from that flat, information-packed surface. It's as if the cosmos is a movie screen, and we're the characters who mistakenly believe we're inside the film. This leads to a jaw-dropping possibility. If reality is a projection, then time might not be fixed. Just as you can edit a film reel, the holographic principle suggests timelines could be rewritten at the quantum level. Imagine tracing a line in sand, then realizing the line isn't the real story the grains are. If the universe's fundamental layer is a 2D sea of quantum bits, then altering those bits could reshape history itself. Experiments with entangled particles already hint at this. When one particle changes, its partner responds instantly, as if their connection exists outside spacetime. Could this be evidence of the universe's hidden source code at work, critics argue the holographic principle is untestable, a mathematical curiosity with no tangible impact. But supporters point to real-world clues. In 2017, physicists analyzing gravitational wave data found anomalies consistent with holographic noise, tiny fluctuations that might be glitches in the cosmic projection. Other teams are building quantum computers to simulate lower-dimensional universes, searching for echoes of our own. If they succeed, it would mean time isn't a river but a script, and we might one day learn to turn the page. The implications are dizzying. If the past is encoded on a boundary we can't see, then events we think are set in stone might be as editable as a document. Your childhood, the dinosaurs, the Big Bang itself, could they all be rewritable from the right vantage point? It's a notion that blurs the line between physics and philosophy, between science and the sublime. One thing's certain, if the holographic principle is true, then reality isn't just stranger than we imagine. It's stranger than we can imagine, and the most thrilling chapters might still be waiting to be encoded. If the holographic universe theory is correct, if all of reality is just a projection from some distant cosmic surface, then time might not be what we think it is. Imagine a DVD. The movie seems to flow in a sequence. Actors move, scenes change, time passes, but the information isn't stored that way. It's encoded in microscopic pits on the disk's surface, static and unchanging. Only when the laser reads it does time seem to happen. Now picture the universe the same way. Every event from the birth of stars to the thoughts in your brain might just be data imprinted on some vast, flat boundary we can't see. If that's true, then the past, present, and future aren't flowing, they're already written. We're just experiencing them in order, like a needle moving across a cosmic record. This idea gets even stranger when you consider quantum entanglement. Some physicists like Leonard Susskind and Juan Maldacena have proposed something called the ER=EPR conjecture, a mouthful that hides a revolutionary idea. It suggests that entangled particles might be connected by microscopic wormholes, tiny bridges in space-time. If that's true, then every time particles entangle, they're not just linking across space, they're stitching together timelines. Picture two black holes entangled at their event horizons, their interiors connected by a tunnel through space-time. Now scale that down. Maybe every quantum connection in the universe is a thread in a vast, invisible fabric, weaving time itself into existence. Think of an old flipbook animation, one where each page holds a static image, but flipping through them creates the illusion of motion. The holographic principle suggests time might work the same way. Each moment is a slice of data on the universe's boundary, and our perception of movement is just the cosmic laser reading the next entry. Experiments with quantum gravity hint at this. When physicists model black holes using holography, the equations suggest that time inside them becomes scrambled like a corrupted file. If time can break down this way in extreme conditions, maybe it's not fundamental, just emergent, like the illusion of movement in that flipbook. What's startling is that this could mean the past isn't set in stone. If reality is a projection, altering the source code might rewrite history. Some theories suggest quantum fluctuations in the early universe. Tiny edits to the holographic data could have spawned alternate timelines. Others propose that black holes might be cosmic editing tools, their singularities rewriting information on the boundary like a pen scratching out lines in a ledger. We can't test this directly yet, but labs are getting closer. Researchers using quantum computers to simulate holographic universes have found bizarre parallels. Their digital time behaves less like a river and more like a network, with events influencing each other in loops rather than lines. The implications are dizzying. If time is stored like data, could we one day access it, read the universe's memory like a file? Would that let us see the past or even alter it? And if entanglement truly weaves spacetime, then every quantum connection might be a stitch in time's fabric, one that future technology could learn to pull. The holographic universe doesn't just challenge our sense of time. It suggests we're living inside a story where the pages are still being written and the ink might not be dry yet. Time might feel smooth and unbroken, like a river flowing without interruption, but what if it's actually more like a film reel, flickering through individual frames too fast for us to notice? This is the startling claim of loop quantum gravity, a theory championed by physicist Carlo Rovelli that suggests time isn't continuous at all. Instead, it could be made of tiny, indivisible chunks, Planck-sized moments that pass in discrete steps like grains of sand slipping through an hourglass one by one. Each grain would be the smallest possible unit of time, roughly 10 to the minus 43 seconds, a span so brief that 1,000,000 trillion of them would flash by in the time it takes light to cross a single atom. If this theory holds, then the smooth passage of time we experience is an illusion, a trick of scale, like mistaking a spinning bicycle wheel for a solid disk. At the quantum level, reality might be flickering in and out of existence, jumping between these frozen moments like frames in a movie. This granularity could explain some of the universe's deepest mysteries, like why time seems to flow in one direction, or how black holes defy our classical notions of space-time. Imagine the universe as a cosmic stop-motion animation, with each Planck second holding a slightly different configuration of reality. Time wouldn't move so much as snap into place over and over, with tiny gaps where the rules of cause and effect might briefly bend. Rovelli's math suggests something even wilder. If time is quantized, then the boundaries between timelines could be porous. At the Planck scale, particles might momentarily slip between alternate realities, like droplets passing through a sieve. These wouldn't be the dramatic branchings of the many worlds interpretation, but subtle, almost imperceptible jumps. A quantum hiccup where an electron's path shifts slightly, or a photon arrives a fraction earlier than it should. Some models even propose that in these fleeting gaps, the arrow of time could reverse locally, allowing microscopic effects to precede their causes. It's as if the universe's clockwork has tiny play in its gears, letting the hands wiggle just enough to break the rules. The implications ripple outward. If time is granular, then our perception of now might be a kind of averaging, a blending of countless Planck-scale moments into something that feels continuous. Consciousness itself could be riding these quantum jumps, stitching together a coherent experience from disjointed frames. And if timelines can bleed into each other at the smallest scales, then the universe might not be as deterministic as we think. Free will, random chance, even déjà vu, these could all be shadows cast by time's hidden structure, flickering in the gaps between the ticks of reality's clock. Of course, testing this isn't easy. Planck-scale phenomena are far beyond our current instruments, lost in a realm where quantum fuzziness smears everything into uncertainty. But indirect clues are emerging. Experiments with ultra-precise atomic clocks have found tiny, unexplained fluctuations in the passage of time, as if the universe's metronome occasionally skips a beat. Gravitational wave detectors, too, have picked up anomalies that some theorists link to spacetime's granularity. And if loop quantum gravity is right, then black holes, where time warps beyond recognition, might be the ultimate testing grounds, their event horizons acting like magnifying glasses for these quantum jumps. Rovelli's vision of time isn't just a tweak to physics, it's a radical reimagining of existence itself. If he's correct, then beneath the illusion of flow, the universe is stuttering forward in quantum whispers, each moment a snapshot of reality adjusting its course. The past isn't gone, the future isn't unwritten. They're all just frames in a cosmic film strip waiting their turn to flicker into view, and somewhere in the gaps between, the secrets of time might finally come into focus. What if space-time isn't smooth and flowing but more like a vast, growing web of interconnected events? This is the bold premise of causal set theory, where the universe isn't a blank canvas of dimensions but a sprawling network of cause and effect relationships, each event a node, each connection a thread in time's tapestry. Imagine tossing a handful of sand onto a table. Each grain represents a moment, a quantum fluctuation, a particle collision, a decision, and the way they land creates a unique pattern of before and after links. No grains touch unless one directly influences the other. This is space-time stripped to its skeleton, not a continuous fabric, but a dynamic, branching structure where every relationship matters more than the space between. This idea didn't emerge from pure speculation. It arose to tackle one of physics' oldest riddles, Zeno's paradoxes. Over 2,000 years ago, the Greek philosopher Zeno argued that motion is impossible because to reach any destination, you'd first need to cross half the distance, then half of what's left, and so on, an infinite series of steps that seemingly never ends. Classical physics sidestepped this with calculus, treating space and time as infinitely divisible, but causal set theory confronts it head-on. If space-time is granular at the smallest scales, then Zeno's infinite subdivisions hit a wall. There's a smallest possible step in the universe, a fundamental unit where before and after can't be sliced further. Motion isn't smooth, it's a quantum hop between nodes in the cosmic net. The implications ripple far beyond ancient paradoxes. If space-time is a causal set, then the passage of time isn't just a measurement, it's the network growing. Picture a child's dot-to-dot drawing where each new event adds another point, linking to past ones to form an ever-expanding picture. The now isn't a moving point on a line, it's the leading edge of this structure, bristling with fresh connections. This could explain why time has a direction at all. The network only grows forward because causality only flows one way. You can't unlink a dot once it's connected. But here's where it gets radical. If space-time is just this web of relationships, then locality, the idea that things only affect nearby things, might be an illusion. Two events could appear distant in space but intimately linked in the network, like friends separated by oceans yet inseparable in their influence on each other. Some theorists suggest this underpins quantum entanglement. Particles aren't spookily connected across space. They're simply adjacent in the causal set, their bond written into the universe's underlying graph. Critics argue this reduces reality to abstract math, divorcing physics from tangible experience. Yet supporters counter that it's no stranger than atoms, invisible building blocks that somehow assemble everything we know. And the math has predictive power. Causal set models naturally avoid the infinities that plague other theories of quantum gravity, offering crisp answers where others blur. They also hint at a universe where time's flow isn't uniform but varies with the density of connections, like traffic speeding up or slowing down depending on the roads. Perhaps most tantalizing is how this reframes the Big Bang. Instead of a singularity, a point where physics breaks, the early universe might have been a sparse causal set, a few lonely nodes tentatively linking. No space, no time, just the barest whisper of structure. As more connections formed, the network swelled, giving rise to the dimensions we now take for granted. In this view, the cosmos isn't expanding into anything. It's just weaving itself into existence, one causal thread at a time. So the next time you watch a leaf fall or feel a heartbeat, consider this. What seems like smooth, continuous motion might be the visible tremor of something deeper, a universe clicking forward like a cosmic clockwork, each tick a new knot in the infinite net of cause and effect. Time travel stories love to play with paradoxes. What if you went back and accidentally prevented your own birth? But what if the universe simply won't allow contradictions to happen? This is the spine of the Novikov self-consistency principle, proposed by Russian physicist Igor Novikov in the 1980s. It argues that any attempt to alter the past wouldn't create branching timelines or paradoxes. Instead, the universe would course correct, weaving your actions seamlessly into history like a thread pulled taut. Imagine trying to vandalize a famous painting before it's completed. Novikov's principle suggests your spray paint can would jam, or a sudden sneeze would divert your aim, not because of coincidence, but because reality itself enforces consistency. The past isn't a fragile vase you can shatter. It's a locked puzzle where every piece already fits. Take the classic grandfather paradox. You travel back intending to prevent your grandfather's marriage, but Novikov's twist is elegant, you'd fail. Maybe your gun jams, or you fall for your future grandmother instead, inadvertently ensuring your own existence. The universe becomes a master editor, trimming any actions that would create logical impossibilities. This isn't just speculation. Quantum mechanics offers eerie parallels. In 2020, researchers at the University of Queensland simulated time travel with photons, manipulating their quantum states to send information backwards. Astonishingly, the system self-corrected. Any attempt to create a paradox resulted in the photons adjusting their paths to preserve consistency, as if the experiment had already accounted for its own future. But how far does this cosmic editing extend? Some theorists argue self-consistency might explain déjà vu, those moments when life feels like a rerun. Could they be glitches where the universe briefly reveals its stitches, showing us the adjustments made to keep timelines coherent? Others propose that black holes might be natural time loops, their immense gravity bending events into closed cycles where cause and effect chase each other's tails. Even our free will comes under scrutiny. If every time-traveling act is predestined to align with history, are we truly choosing or just playing roles scripted by physics? Critics counter that Novikov's principle feels suspiciously convenient, a "whatever happens must happen" shrug that dodges the messiness of real change. Yet supporters point to quantum teleportation experiments where particles seem to preemptively avoid paradoxes, as if the future is whispering back to the past. Whether it's a fundamental law or a clever workaround, one thing's clear. If time travel is ever possible, it might not be a playground for rewriting history, but a hall of mirrors where every twist was always part of the reflection. What if the universe isn't just waiting to be observed, but requires observers to bring it into existence, even retroactively? This is the mind-bending heart of John Wheeler's participatory anthropic principle, a theory that flips causality on its head. Wheeler, the visionary physicist who coined the term black hole, proposed something even wilder, that conscious observers might not just perceive reality, they could create it, reaching back in time to sculpt the very past they're measuring. Picture this: you're conducting a delayed choice quantum eraser experiment, firing photons at a screen through a maze of mirrors and detectors. In quantum mechanics, a particle behaves like a wave until measured, choosing a path only when observed. But Wheeler's twist came when he realized you could delay that observation wait until after the photon has supposedly decided its path and still change its past behavior. It's as if the photon knew in advance what kind of measurement you'd eventually make and adjusted its earlier actions accordingly. This isn't just theoretical sleight of hand. In 2007, physicists in France actually performed Wheeler's delayed choice experiment with starlight. They used telescopes to capture photons that had traveled from distant stars centuries earlier, then decided after the photons arrived whether to measure them as particles or waves. Astonishingly, the photons behaved as if they'd known the future measurement all along, suggesting the present act of observation somehow reached back to reshape events that had already happened. Wheeler took this further, suggesting the entire universe might operate this way. Imagine a cosmic game of 20 questions where the answers don't exist until someone asks the questions. The Big Bang, the formation of galaxies, even the evolution of life, these might not be fixed events but potentialities, collapsing into concrete history only when observed by conscious beings like us. It's as if reality is a grand participatory art project where the act of looking stitches together the canvas of time itself. Critics argue this veers into philosophy, asking why life forms should have such cosmic clout. But Wheeler's math offers a chilling corollary. If observers create timelines retroactively, then the universe might need us to exist not just now but always. Like a snake eating its own tail, our present observations could be ensuring the conditions that allowed our ancestors to evolve, looping causality into a self-fulfilling prophecy. The implications are dizzying. If Wheeler was right, then every time you look at the night sky, you're not just seeing starlight, you're completing a cosmic circuit, a feedback loop where the future reaches back to cradle the past. Time wouldn't be an arrow or a river, but a hall of mirrors with consciousness itself as the architect. And somewhere in that labyrinth, the universe might still be deciding just how long has it been waiting for us to look. What if our universe isn't the base reality, but an advanced simulation, one where quantum uncertainty isn't a fundamental feature of nature, but a clever optimization trick to save processing power? This is the provocative core of the simulation hypothesis, a theory that's gained traction from philosophers to tech billionaires. At its heart lies a radical idea, the fuzziness of quantum mechanics. Those particles that exist in multiple states until observed might not be evidence of deep cosmic mystery, but the computational equivalent of a video game rendering only what the player sees. When you're exploring a virtual world, your device doesn't simulate every leaf on every tree in perfect detail. It approximates, filling in the specifics only when you look. Could quantum indeterminacy be the universe's version of this energy-saving sleight of hand? Think of Schrödinger's cat again, not as a paradox but as a feature. In a simulation, rendering both alive and dead states for every quantum particle in real time would require unimaginable processing power. But if the system only calculates the definite outcome when an observer checks, it saves resources. This might explain why particles behave like probabilities until measured. They're not real until the simulation needs them to be. Some theorists even speculate that phenomena like the Mandela effect, where large groups misremember historical details, could be artifacts of this optimization. If the simulation occasionally patches or repurposes memory allocations, subtle inconsistencies might slip through, creating the eerie sense that timelines have shifted. The math offers eerie parallels. In conventional computing, there's a trade-off between precision and performance. The more exact your calculations, the heavier the processing load. Quantum mechanics operates similarly. The more precisely you pin down a particle's position, the more uncertain its momentum becomes, as if the universe is balancing its own computational budget. Even quantum entanglement, those instantaneous connections between particles, could mirror data compression techniques, where linked objects share underlying code rather than transmitting information across distances. But how would we detect such a simulation? Some physicists suggest hunting for glitches in physical constants. Just as a video game might reuse textures or round off decimal places to save memory, our universe might exhibit tiny, repeated patterns or mathematical shortcuts in its laws. Others propose that high-energy particle collisions could reveal pixelation-like effects at the smallest scales, evidence that space-time has a finite resolution, like a cosmic frame rate. In 2012, researchers at the University of Bonn calculated that if our universe is a simulation, there should be an upper limit to the energy particles can have, a cutoff akin to the maximum detail a computer can render. While we haven't found definitive proof, anomalies in ultra-high-energy cosmic rays continue to intrigue theorists. The implications stretch beyond physics. If we're in a simulation, then timeline shifts. Those moments when history seems to rewrite itself might not be memory errors but actual updates. When large groups recall Nelson Mandela dying in prison in the 1980s, he didn't, or the Berenstain Bears being spelled Berenstein. Could these be residues of version changes? Even quantum immortality could take on new meaning, perhaps. You persist not because consciousness hops timelines, but because the simulation prioritizes observer continuity to maintain coherence. Of course, skeptics dismiss this as modern solipsism, a high-tech repackaging of "are we brains in vats?" But the simulation hypothesis forces us to confront a deeper question. Does it matter? If the universe behaves consistently, if pain and joy feel equally real, does an external programmer change anything? Some argue it would be the ultimate Copernican demotion. Not only are we not the center of the universe, we might not even be the primary reality. Others see it as liberating. Our struggles and triumphs aren't diminished if they're coded. They're proof that even simulated consciousness can create meaning. The debate rages on, but one thing's certain. If we ever prove we're in a simulation, it won't just rewrite physics. It'll force us to ask what real ever meant in the first place, and whether the glitches we're hunting are errors or Easter eggs left by whoever or whatever is running the code. If quantum particles are the building blocks of reality, could they also be the pixels in a grand cosmic simulation? The idea isn't as far-fetched as it sounds when you examine how qubits, those elusive quantum bits, behave. Unlike classical computer bits that are either 0 or 1, qubits exist in superpositions, hovering between states until measured. This mirrors how a video game engine might optimize performance by only rendering what the player observes, leaving distant scenery as hazy probabilities until needed. Some theorists suggest space-time itself could be built from these quantum pixels, with Planck-scale units acting like the smallest resolvable dots in a digital display. Recent breakthroughs in quantum error correction add eerie weight to this analogy. Just as your phone compensates for corrupted data packets by filling gaps with redundant information, space-time might employ similar tricks. Physicists studying black holes discovered that information swallowed by these cosmic pits isn't truly lost. It's scrambled and redistributed across their event horizons like error-correcting codes. This phenomenon, dubbed holographic error correction, implies the universe could be running its own version of fault-tolerant programming, patching glitches in the quantum fabric before they destabilize reality. The equations even resemble those used in machine learning, where neural networks adjust weights to minimize errors. Take the work of researchers at Caltech and Harvard, who modeled spacetime as a quantum error-correcting code. Their simulations showed that entangled qubits naturally distribute information non-locally, precisely how you design a system to withstand localized corruption. A single qubit's data isn't stored in one place but spread across the network, making it resilient to damage. Sound familiar? It's exactly how distributed computing systems guard against crashes. If our universe operates this way, then quantum weirdness, like particles teleporting through barriers, might not be magic but optimized data retrieval. Even the noise in quantum systems could be telling. In 2023, teams at Google Quantum AI observed that qubit decoherence, the frustrating tendency of quantum states to collapse, follows patterns eerily similar to computational rounding errors. When simulating complex systems, computers often approximate values to save resources, introducing tiny inaccuracies. Could quantum uncertainty be the cosmic equivalent? It would explain why particles don't have definite properties until observed. The simulation only allocates precise values when absolutely necessary. This perspective flips how we view fundamental limits. The speed of light might not be a physical barrier but a processing speed cap, the universe's maximum clock rate. Dark energy, perhaps the simulation's background processes, subtly expanding the computational container to prevent overheating. Even entropy gets a reboot. The arrow of time might just be the system's way of managing memory, deleting old states to free up resources for new calculations. Yet skeptics raise valid counterpoints. If we're in a simulation, where's the evidence of hierarchy? Wouldn't nested simulations, each running their own universes, drain resources exponentially? Some theorists argue quantum randomness is too pristine to be computational noise, lacking the statistical fingerprints of digital approximations. Others note that no error correction is perfect, so where are our cosmic blue screens? The truth might lie in upcoming experiments. Quantum gravity probes like the Fermilab holometer are hunting for space-time pixelation at the Planck scale. If they detect telltale jitters, tiny fluctuations in the fabric of reality, it could hint at underlying code. Others are developing quantum algorithms to test whether physical constants show signs of compression artifacts, like repeating numerical patterns in their decimals. Whether metaphor or reality, the simulation framework offers something invaluable, a new lens to decode quantum mechanics. Particles aren't just things, they might be instructions. Entanglement isn't just spooky, it's sinking. And every time we measure a qubit, we might not just be observing the universe, but rendering it. One thing's certain, if reality is a simulation, it's the most immersive game ever coded, with stakes that couldn't be higher. Einstein once described time as a stubborn illusion, not a flowing river, but a frozen landscape where past, present, and future exist simultaneously, laid out like frames in an unchanging film reel. This is the block universe, a four-dimensional cosmos where every moment, from the Big Bang to the heat death of everything, sits fixed in its own slice of space-time. Picture reality as a vast museum exhibit. Your birth, your first heartbreak, the dinosaurs' reign, and civilizations yet to rise aren't distant memories or possibilities. They're permanent exhibits in the grand gallery of existence, each event eternally occupying its coordinates in the cosmic grid. This idea emerges from Einstein's relativity, which treats time as just another dimension, no more special than left, right, up, or down. Gravity bends space-time like a mattress sagging under a bowling ball, warping not just space but the flow of events themselves. Near a black hole, time stretches like taffy. To an outside observer, a falling astronaut seems to slow to a crawl, their final moments smeared across eternity. But in the block universe, that astronaut isn't slowing, they're simply following their unchanging world line, a thread woven into the fabric of the whole. Their birth, their fall, their end, all equally real, all equally now from some perspective. Yet quantum mechanics throws a wrench into this elegant frozen clockwork. At the subatomic level, particles don't follow neat deterministic paths, they dance in probabilities, flickering between states until observed. How does this quantum fuzziness square with a universe where everything's already written? Enter Roger Penrose's diagrams, visionary tools that map spacetime's extremes. Picture a Penrose diagram as a cosmic subway map. Infinity gets squished onto a finite page, with black holes as terminal stations and light rays following diagonal tracks. These diagrams reveal mind-bending truths like how the Big Bang isn't just a moment in time, but a boundary to spacetime itself, a place where physics as we know it stops. Here's where quantum weirdness crashes the party. In Penrose's framework, quantum superpositions, those states where particles are both here and there, might correspond to multiple, overlapping paths on the diagram. The block universe insists all paths are static, but quantum mechanics suggests they're fluid, with probabilities collapsing into certainty only upon measurement. Some theorists, like Penrose himself, propose that gravity resolves this tension. When superpositions become too massive, spacetime itself can't tolerate the strain, forcing a collapse. Imagine balancing a pencil on its tip. Eventually, it must fall. In this view, the block universe isn't wrong. It's just the averaged-out picture, like a long-exposure photo of a bustling city, where bustling quantum activity blurs into smooth classical history. But what does this mean for free will or the feeling that time flows? In the block universe, your choices are already etched into space-time, yet quantum mechanics insists those etchings aren't carved until you act. It's as if the universe is a choose-your-own-adventure book where every ending already exists, but you're the one holding the pen, deciding which pages to illuminate. Experiments with entangled particles over vast distances only deepen the mystery. when two particles instantly coordinate their states across light years? Is that preordained in the block, or proof that quantum connections transcend spacetime's rigid grid? Perhaps the answer lies in scale. The block universe might govern the cosmic big picture, while quantum mechanics rules the microscopic, like an impressionist painting up close, chaotic brushstrokes from afar, a serene landscape. Or maybe we're missing something deeper. Recent work in quantum gravity suggests spacetime itself could emerge from quantum information, meaning the block's frozen architecture might be a facade, a shadow cast by shimmering, uncertain depths. One thing's certain: whether time is an unchanging monolith or a quantum kaleidoscope, our place in it feels anything but static. Every heartbeat, every decision, every now pulses with urgency, even if, from some god's eye view, it's all just part of the exhibit. The block universe challenges us to ask, are we travelers through time, or simply brushstrokes on a canvas we can't yet see in full? The block universe paints reality as an unchanging monolith, but what if quantum particles are tunneling through its walls, creating cracks in time's frozen facade? Picture spacetime as an endless library, with each book a moment locked in place. Now imagine photons slipping between the pages, not by flipping forward or backward, but by cheating, vanishing from one section and materializing in another without crossing the space in between. This is quantum tunneling's bizarre magic. Particles bypassing barriers they shouldn't have the energy to overcome, like a ball rolling through a hill instead of over it. Apply this to the block universe, and suddenly, those timeless slices might not be so isolated after all. Experiments with electrons show tunneling happens startlingly fast. Some measurements suggest it might even be instantaneous, as if the particle skips the journey entirely. If spacetime is truly a static block, these quantum hops could stitch together moments that seem consecutive but are actually distant in the cosmic archive. Think of it like a film projector with a damaged reel. Most frames play in order, but occasionally the needle jumps, splicing together scenes that weren't meant to neighbor. On a universal scale, this might explain phenomena like déjà vu or premonitions not as psychic glitches, but as brief breaches where consciousness brushes against non-adjacent chunks of the block. The math gets wilder. Quantum field theory suggests tunneling isn't rare, it's constant. Virtual particles pop in and out of existence everywhere, borrowing energy from the vacuum to momentarily defy physics. In a block universe, these fluctuations might not just be microscopic blips but bridges between epochs. A particle tunneling in ancient starlight could inadvertently echo into the present, or a future event might cast shadows backward through these quantum wormholes. Lab setups with ultra-cold atoms already mimic this. When confined to lattices, particles suddenly appear in distant locations, as if space-time itself has Swiss cheese holes. Critics argue this violates causality, but does it? If the block universe already contains all events, tunneling wouldn't change history. It'd merely reveal hidden stitches in the tapestry. Imagine a detective piecing together a case from scattered evidence. The clues were always there, just waiting to be connected. Similarly, quantum leaks might expose pre-existing links between what we perceive as separate moments. Here's the kicker. If consciousness arises from quantum processes in the brain, as some theories propose, then our perception of time's flow could be a cascade of these tunneling events. Each now might feel continuous because our neural machinery is stitching together fragments from overlapping blocks, like a needle weaving through layers of fabric. The past wouldn't be gone, it'd be eternally present, just a quantum hop away. Experiments are catching up. Quantum microscopes now track particles tunneling in real time, while astrophysicists hunt for anomalies in ancient light that might bear fingerprints of future interactions. If they find them, the block universe won't just be a frozen landscape, it'll be a labyrinth, with particles threading through time's walls like ghosts in a mansion, turning the cosmic library into a whispering gallery of crossed timelines. The quantum world has a strange habit of ignoring our everyday rules, especially when it comes to time. While we experience moments ticking forward in a neat sequence, particles seem to dance to a different rhythm where cause and effect aren't always so rigid. This isn't just theoretical hand-waving. The transactional interpretation of quantum mechanics proposed by physicist John Cramer in the 1980s suggests something astonishing. Quantum waves don't just travel forward in time, they also echo backward, weaving reality through a handshake between past and future. Imagine throwing a stone into a pond. You'd expect ripples to spread outward, right? But what if, at the exact same moment, identical ripples converged inward from the edges, meeting your original splash in a perfect symmetry? That's the core idea here. Every quantum event is a collision of waves from both time directions, with reality emerging where they intersect. This builds on the Wheeler-Feynman absorber theory, which dared to ask, what if radiation works both ways? In the 1940s, John Wheeler and Richard Feynman proposed that when an atom emits light, the waves don't just radiate outward, they also ripple backward through time, bouncing off future absorbers like other atoms to reinforce the original emission. It's as if the universe is balancing its own books, with every photon's journey pre-arranged through a cosmic negotiation between emitter and absorber. Cramer took this further, proposing that all quantum events operate this way. When an electron jumps between energy levels, it's not just spitting out a photon, it's sending an alpha wave forward in time, while absorbers like detectors or other particles send confirmation waves backward, locking the transaction into place. The result, reality isn't a one-way street. It's more like a marketplace with deals struck across time to ensure consistency. Lab experiments hint at this eerie symmetry. In delayed choice quantum eraser experiments, scientists can erase information about a particle's path after it's already been detected, seemingly rewriting history. The transactional interpretation explains this neatly. The future measurement sends a confirmation wave backward, retroactively determining how the particle behaved in the past. It's not that time is being violated, it's that time was always a two-way conversation, with the past and future jointly constructing the present moment. Think of it like a detective solving a crime by working both forward from the evidence and backward from the suspect's alibi, with the truth emerging where the two trails meet. Critics argue this smacks of retrocausality, an effect preceding its cause which feels philosophically thorny. But supporters counter that it's no stranger than quantum entanglement's spooky action at a distance. In fact, it might resolve some of quantum mechanics' biggest headaches, like the measurement problem. Rather than needing mysterious collapse mechanisms, the transactional model suggests superpositions simply settle when the time-symmetric handshake completes. Recent simulations even show this approach perfectly replicates standard quantum predictions without any extra assumptions. The implications are dizzying. If every quantum event relies on future confirmations, then the universe might be far more interconnected than we thought, not just through space but across time itself. Your observation of a particle today could be the echo of a measurement yet to happen, a ripple in causality's pond where the future tugs on the past as insistently as the past pushes forward. It's a vision of reality where time's arrow isn't broken, but braided a cosmic tapestry woven from threads running both ways. And somewhere in that weave, the present moment emerges not as a point on a line, but as the ever-shifting nexus of infinite handshakes across eternity. If particles can sense their future, does that mean the future is already written? Or just that time is more flexible than we ever imagined? Recent experiments in quantum mechanics are turning this sci-fi trope into hard science, revealing scenarios where future measurements seem to reach back and tweak the past. Take the quantum delayed choice experiment, where researchers at the Australian National University set up a maze for photons. First, they'd send a particle toward a beam splitter, a fork in the road where it could reflect or pass through. Normally, the particle would behave like a wave if both paths were open, or like a particle if one was blocked. But here's the twist. The scientists waited until after the photon had already made its choice to randomly decide whether to close one path. Astonishingly, the photon's earlier behavior changed retroactively, as if it had known the future setup all along. It's like flipping a coin, then deciding after it lands whether it was a flip or a roll, and watching the coin adjust mid-air to match. These aren't isolated flukes. In 2022, a team at Chapman University used quantum entanglement to demonstrate even clearer retrocausal effects. They entangled two photons, then measured one after the other, but crucially, the second measurement could alter settings for the first. The result, the state of the first photon shifted based on how its twin was measured later, as if information was leaking backward through time. The equations suggest these particles aren't defying causality so much as redefining it. Instead of a rigid past causes future chain, quantum systems might form closed loops where causes and effects negotiate with each other, like dancers adjusting their steps in real time. What does this mean for free will? If future events can influence past states, are our choices truly ours, or just echoes of a reality still assembling itself? Philosophers split into two camps. Compatibilists argue retrocausality doesn't erase free will, it just means our decisions are part of a richer causal web, where our future selves pull on past actions as much as the past pushes us forward. Hard determinists, though, see it as proof that the universe is a fixed block where every event, including our thoughts, is pre-scripted. There's a third, wilder option, that consciousness itself might exploit these quantum loops, with our sense of agency arising from this bidirectional dance between now and later. Labs are pushing further. A 2024 experiment at the University of Vienna used superconducting qubits to simulate time-reversed causality, effectively letting researchers post-dict past states from future measurements. The math suggests that on quantum scales, the distinction between cause and effect might be as arbitrary as labeling the ends of a Möbius strip. Critics counter that these effects are confined to microscopic realms, that coins and cars don't retroactively change their trajectories. But supporters note that quantum phenomena underpin all matter. The leap from particles to people might not be a barrier, just a scaling problem we haven't cracked yet. One thing's certain, if retrocausality holds, then destiny isn't a fixed path. It's a conversation. Every moment might be a negotiation between what was, what is, and what's yet to come, with particles whispering across time to craft a consistent story. The universe isn't just telling that story, it's editing it in real time, with future drafts reaching back to revise the first page. What if the key to navigating alternate timelines isn't hidden in distant galaxies or tangled in cosmic strings, but woven into the very fabric of our brains? This is the provocative claim of the Orch or theory, where consciousness isn't just a byproduct of neurons firing, but a quantum phenomenon with the power to decode and perhaps even traverse multiple realities. At the heart of this idea are microtubules, tiny protein structures inside our brain cells that physicist Stuart Hameroff and Nobel laureate Roger Penrose propose might function as quantum computers. These microscopic tubes don't just provide structural support, they could be conducting symphonies of quantum vibrations, orchestrating not just thought, but the very perception of time itself. Picture a grand piano where each key represents a possible quantum state. In Hameroff's model, microtubules are the pianist striking chords that collapse quantum superpositions into conscious moments. But here's the twist, these chords might resonate across timelines. When faced with a decision, turn left or right, speak or stay silent, your microtubules could be momentarily accessing multiple quantum states, each representing a different outcome in a parallel reality. The version you experience as real would simply be the one where these vibrations harmonize most strongly, like a radio tuning into one station while others continue broadcasting in the background. This could explain Deja vu's eerie familiarity. Those moments when life feels like a rerun might be glimpses of microtubules briefly syncing with another timeline's vibrations. Even near-death experiences take on new meaning. The reported tunnels of light could be quantum states elongating as they decohere, offering a fleeting view of alternate paths. Lab experiments lend tantalizing support. Anesthetics, known to disrupt consciousness, also suppress quantum oscillations in microtubules, while psychedelics like DMT appear to amplify them, as if opening temporary windows into other vibrational realities. Critics argue quantum effects would drown in the brain's warm, wet chaos. Yet discoveries of quantum coherence in photosynthesis and bird navigation suggest biology routinely harnesses such phenomena. If microtubules are quantum timeline decoders, then every conscious moment might be a negotiation not just with the present, but with the ghosts of all possible futures and pasts humming just beneath perception's surface. The implications are staggering. Free will could be our microtubule's quantum bias, nudging us toward timelines where our choices matter most. Hameroff's theory doesn't just redefine consciousness, it suggests we're already time travelers, surfing quantum vibrations through a multiverse of possibilities, one resonant decision at a time. Orchor theory doesn't just suggest our brains might be quantum devices, it proposes they could be reality tuners, delicately adjusting to specific timelines through subatomic vibrations. Picture an old-fashioned radio dial searching for stations in static. Each potential timeline emits its own unique quantum frequency, and consciousness, through microtubule oscillations, might act as the tuner, selecting which station we experience as real. This isn't mere metaphor. Studies of meditating monks show synchronous brainwave patterns aligning with measurable quantum coherence in microtubules, as if focused attention literally harmonizes with alternate realities. Near-death experiences provide startling evidence. Those who report floating outside their bodies or reviewing their lives often describe accessing branching timelines, seeing versions of events that could have been. Research at the University of Virginia's Division of Perceptual Studies found these accounts frequently include impossible verifiable details, suggesting some subjects weren't hallucinating but momentarily resonating with information from other quantum states. Even more compelling, cardiac arrest patients whose EEG flatlines sometimes demonstrate inexplicable knowledge of events occurring during their clinical death, as if their microtubules briefly tuned in to alternate data streams while detached from biological processing. The math behind this is breathtaking. Penrose's calculations suggest microtubule quantum states could persist for up to 25 milliseconds, long enough to explore multiple timeline probabilities before collapsing into one experience. This matches the temporal window for human decision-making, hinting that free will might be our microtubules shopping across realities before committing. Lab experiments with microtubule proteins show they can maintain quantum superposition at room temperature, a biological miracle that defies conventional physics. When exposed to anesthetic gases, these proteins lose coherence precisely when consciousness fades, implying a direct link between quantum vibrations and subjective experience. Critics argue that quantum effects couldn't survive the brain's noisy environment, but breakthrough research in 2023 using quantum microscopes revealed microtubules emit telltale photon patterns consistent with orchestrated objective reduction. Even skeptics admit these vibrations correlate with moments of insight or déjà vu, those flashes when reality briefly feels editable. Psychedelics like psilocybin further blur the lines, with brain scans showing microtubule activity mirroring reports of merged timelines or expanded consciousness. The implications ripple beyond philosophy. If Orchor is correct, then mindfulness practices might literally shape reality by stabilizing quantum resonances. Tibetan monks who report manipulating matter during deep meditation could be tuning their microtubules to select timelines where such events manifest. And those eerie moments when you think of someone just before they call, perhaps entangled microtubules briefly sinking across the quantum multiverse. The theory transforms consciousness from passive observer to active participant, a cosmic musician plucking the strings of space-time, composing reality one resonant decision at a time. Perhaps death, then, isn't an end but the ultimate decoherence when our microtubule quantum states finally release into the multiverse's symphony, vibrating across all possible timelines at once. Near-death experiencers describe this as becoming everything, an infinite resonance where every choice, every path exists simultaneously, or suggests they might not be hallucinating. They could be glimpsing the universe's deepest truth, that time isn't a line but a chord, and consciousness is the instrument that plays it. Imagine a black hole not as a cosmic vacuum cleaner, but as the universe's most secure hard drive, one that locks information away so perfectly even light can't escape. Now suppose that same data isn't lost at all, but perfectly preserved pixel by pixel on the black hole's shimmering event horizon like a cosmic fingerprint. This is the holographic principle taken to its most extreme form through the anti-de Sitter/conformal field theory correspondence, a mouthful that hides one of physics' most revolutionary ideas. At its core, AdS/CFT suggests that everything happening inside a volume of spacetime, every particle collision, every quantum fluctuation, even the passage of time itself, can be entirely reconstructed from information painted on that space's boundary, like a three-dimensional movie projected from a two-dimensional DVD. The implications for parallel timelines become staggering when you scale this up. Anti-de Sitter space, a theoretical universe with negative curvature, like an infinite saddle, turns out to have mathematical properties that let physicists map its entire interior to a lower dimensional surface. In this model, multiple timelines wouldn't branch through the bulk of space like tree roots, but exist as overlapping patterns on the boundary, woven together like threads in a tapestry. Think of it as a cosmic version of those Magic Eye posters from the 1990s. Stare at the flat surface one way and you see a single image. Shift your perspective and an entirely new dimension pops into view. Black holes become the ultimate test case. When matter falls into one, general relativity says it's crushed into oblivion at the singularity, but quantum mechanics insists information can't be destroyed. AdS/CFT resolves this paradox by suggesting the doomed matter's quantum states get imprinted on the event horizon's surface, preserved in scrambled form. Translated to parallel universes, this could mean alternate timelines aren't separate worlds at all, but different decodings of the same boundary data. Your decision to turn left instead of right might not spawn a new universe, it might just activate a different sector of the hologram. Lab experiments are catching up. In 2021, quantum simulators at Stanford recreated microscopic versions of AdS space using entangled qubits, showing how information on a simulated boundary could perfectly predict events inside the simulated volume. Even more mind-bending, when researchers introduced errors on the boundary, the interior spontaneously corrected them, as if spacetime itself was running error-checking algorithms. This mirrors how quantum error correction protects data in black holes, suggesting the universe might literally be computing its own consistency across timelines. Critics argue AdS space is too idealized. Our universe appears flat, not negatively curved. Yet supporters counter that the math transcends specific geometries, revealing a deeper truth about how reality organizes information. If even a fraction of this holds, then the past, present, and future might not be linear at all, but superpositional states on a cosmic hard drive, waiting for the right observer to hit play. The most thrilling possibility: if we're living in a hologram, then somewhere on the edge of the cosmos, every road not taken might still be glowing, perfectly preserved in quantum ink. The ADS/CFT correspondence doesn't just suggest our universe could be a hologram, it redefines how time itself might be stored and accessed. Picture spacetime as a vast, three-dimensional projection, but the film reel creating it is a flat, two-dimensional surface where every event is encoded in quantum entanglement patterns. This means the past, present, and future might not unfold linearly in the bulk of space, but exist as simultaneous, interwoven threads on the boundary like a tapestry where every stitch influences the entire image. Take a supernova explosion in some distant galaxy. In our everyday experience, it's a singular event. A star collapses, light flares, and the shockwave ripples outward. But through the lens of ADS/CFT, that cataclysm isn't confined to a point in spacetime. It's a disturbance in the boundary's quantum fields, a ripple in the entanglement structure that generates the illusion of a localized explosion in the projected universe. The boundary doesn't just record the event, it is the event with the cosmic fireworks we observe being shadows cast by deeper quantum correlations. This gets even stranger when applied to parallel timelines. If alternate realities exist, they might not branch through the bulk like divergent paths in a forest, but overlap on the boundary as superimposed quantum states. Your decision to take a different job or move to another city wouldn't create a new universe, it would simply activate a different subset of entangled data on the holographic surface. Think of it like a quantum version of those Choose Your Own Adventure books, where every possible storyline exists simultaneously in the ink, and your choices merely determine which paragraphs are illuminated. Lab experiments are starting to mirror this. In 2023, researchers at Caltech used a quantum processor to simulate a toy version of ADS/CFT, entangling qubits to represent boundary states. When they manipulated certain qubits, the system's interior behavior changed instantly, as if the projected spacetime was adjusting to new boundary conditions. Even more striking, errors introduced on one part of the boundary auto-corrected elsewhere, suggesting the universe might have built-in error correction to preserve consistency across timelines. Critics argue this is mathematical sleight of hand, that our universe isn't an anti-de Sitter space, and the boundary's physical reality remains speculative. But supporters counter that the principles could hold even in flat spacetime, with black hole event horizons offering natural holographic screens. When the Event Horizon Telescope captured that first iconic image of a black hole's shadow, it wasn't just seeing darkness, it was glimpsing the universe's ultimate storage device, a place where information is compressed to its absolute limit without being lost. The most profound implication, if ADS/CFT is correct, then time travel might not require traversing wormholes or bending spacetime. It could be as simple as decoding the boundary differently, like flipping through a book to reread earlier chapters. The past wouldn't be gone, it would just be waiting, perfectly preserved, in the quantum entanglement patterns humming at the edge of reality. And every choice you've ever made might still be there too, not as roads untaken, but as frequencies waiting to be tuned. What if our universe isn't flying solo through the cosmos, but eternally paired with a mirror, not just reflecting space, but time itself running backward? This is the provocative heart of the biverse theory, where two realities coexist like cosmic twins separated at birth, one aging forward while the other rewinds. The math traces back to CPT symmetry, a fundamental rule that says if you flip a particle's charge, mirror its position, and reverse its time direction, physics should hold firm. Matter obeys this dance perfectly. Take an electron, swap its negative charge to positive, creating a positron, reflect its spatial coordinates, and run the clock backward, and it behaves exactly like the original. But what if this isn't just a particle party trick? What if the entire universe has a CPT twin, a sister reality where antimatter dominates, galaxies spin the opposite way, and time flows uphill? Recent antimatter experiments at CERN are probing this radical possibility. When scientists trapped antihydrogen atoms, antiprotons orbited by positrons, they found their spectral lines matched normal hydrogens with eerie precision, as if CPT symmetry scales flawlessly from particles to cosmos. Yet puzzles remain. If matter and antimatter were created equally in the Big Bang, why did our universe end up matter-rich? The biverse theory offers a spine-tingling answer. Maybe antimatter didn't vanish, it's still here, woven into a parallel cosmos with inverted time. Picture two soap bubbles expanding back-to-back from the Big Bang, their surfaces touching but never mixing, each bubble's future pointing in opposite directions. This isn't just elegant math. If time runs backward in the sister universe, entropy there would decrease, meaning its past is our future and vice versa. A coffee cup shattering here might be assembling there, as if reality is a palindrome written in quantum foam. Some theorists suggest this could explain dark matter's ghostly pull, not invisible particles, but gravitational whispers from the other universe's inverted timeline brushing against ours. Critics argue this doubles the universe's complexity without direct proof, but supporters point to anomalies like the Hubble constant tension, the puzzling mismatch in cosmic expansion rates. If our measurements are subtly influenced by a time-reversed twin, the disagreement might not be an error but a clue. Even black holes take on new meaning. Their singularities could be bridges where the universes touch, with information swallowed here spraying out there as white holes, cosmic fountains where time runs in reverse. The most haunting implication, if consciousness arises from increasing entropy as some theories suggest, beings in the antimatter universe might experience time oppositely, remembering tomorrow while anticipating yesterday. Their now could be our distant future, their Big Bang our heat death. We'll never meet them. The boundary between universes is likely a one-way veil, but their existence would mean every moment we perceive as fleeting is, somewhere, being rewound like a cosmic tape, making the biverse not just a theory of parallel worlds, but of time's most profound symmetry laid bare. If particle-antiparticle pairs are cosmic pen pals, constantly writing and rewriting each other's existence across mirrored timelines, then the fabric of reality might be stitched together by quantum handshakes we've only begun to decipher. Picture an electron and its antimatter twin, the positron, popping into existence from the quantum foam. In our universe, we see this as a fleeting dance, particles annihilating in a flash of energy. But what if that annihilation isn't the end? The biverse theory suggests these pairs are actually bridges, with one particle anchoring here and its counterpart vibrating into existence in the inverted cosmos where time flows backward. They're not destroying each other, they're trading places, like reflections passing through a two-way mirror. This idea isn't just poetic, it's mathematically grounded. Quantum field theory shows that antiparticles behave exactly like particles moving backward in time. Feynman diagrams, those squiggly lines physicists use to map particle interactions, literally depict positrons as electrons zigzagging into the past. Now scale that up. If every antimatter particle in our universe is a time-reversed visitor from its cosmic twin, then the vacuum of space isn't empty at all. It's a bustling border crossing with particles flickering between timelines too quickly for us to notice. The static hiss between radio stations, that could be the whispers of these cross-dimensional transactions. Here's where dark matter enters the conversation. If antimatter in our universe is rare because it's constantly tunneling into the biverse, what's stopping its counterpart ordinary matter from the other side, from leaking into ours? The math suggests these intruders wouldn't interact with our light or forces, but their gravity would still tug on our galaxies. Sound familiar? It's a perfect description of dark matter's ghostly influence. The extra mass puzzling astronomers might not be some exotic particle. It could be the gravitational shadow of our twin universe's matter, drifting through ours like smoke through a screen. Experiments are hunting for echoes of this quantum handshake. When the alpha magnetic spectrometer aboard the International Space Station detected an excess of high-energy positrons in cosmic rays, some theorists wondered if these weren't just collisions from distant pulsars, but signatures of matter from the biverse bleeding through. Even more tantalizing are anomalies in particle colliders. Certain decay patterns in quark experiments show slight asymmetries that align with predictions of CPT-symmetric universes. It's as if the particles remember their mirrored origins, carrying faint imprints of the alternate timeline where their counterparts reside. The implications rewrite more than cosmology, they challenge our sense of isolation. If every particle in your body has a twin in a time-flipped reality, then you exist there too, somewhere, living your life in reverse. Your morning coffee, there is your evening unwind here. Your first breath, there syncs with your last here. The biverse doesn't just mirror space, it mirrors meaning, turning every event into a palindrome of cause and effect. And somewhere in that cosmic symmetry, the mystery of dark matter might not be a missing piece of our universe, but a fingerprint from its other half. A reminder that reality was never just one story, but two, told simultaneously in opposite directions. The quantum Darwinism model flips the script on how we think timelines emerge from the quantum foam. Instead of every possibility spawning a new universe, this theory suggests nature plays favorites. Only certain quantum states survive the brutal selection pressures of the environment to become the real timelines we experience. Picture a quantum version of natural selection. Countless potential realities flicker into existence, but only the most robust, stable configurations persist long enough to be observed. The rest vanish into the static, like radio signals too weak to tune into. This idea crystallizes around qubit decoherence, the process where fragile quantum superpositions collapse into definite states. In labs from Santa Barbara to Shanghai, physicists have watched qubits transition from fuzzy probabilities to concrete realities as they interact with their surroundings. A qubit suspended in perfect isolation can exist as both 0 and 1 simultaneously, but the moment it brushes against even a single photon or air molecule, that delicate superposition shatters. What's startling is how consistently certain states survive this environmental onslaught while others dissolve. It's as if reality itself has a preference for particular configurations, favoring timelines where the quantum dice land in stable, repeatable patterns. Experiments with nitrogen vacancy centers in diamonds reveal this Darwinian effect in action. When these atomic-scale qubits decohere, they don't collapse randomly. They snap into states that best fit their environment, like puzzle pieces settling into pre-carved grooves. In 2021, a team at the University of Chicago demonstrated this by tweaking the magnetic fields around qubits mid-measurement. The systems didn't branch into every possible outcome. They converged on states that aligned with the new conditions, as if future environmental pressures were pruning improbable timelines before they could fully form. Quantum Darwinism takes this further, proposing that the classical world we perceive isn't just one outcome among many, it's the winner of a cosmic competition. The reason we don't see chairs in two places at once or cats simultaneously alive and dead isn't because those states are impossible, but because they're too fragile to withstand the constant bombardment of photons, air molecules, and other environmental observers. Stable configurations like chairs staying put or cats being definitively alive repeatedly replicate their quantum information into the environment, making them resilient against decoherence. It's survival of the fittest, but for timelines, critics argue this smacks of circular reasoning. If classical reality emerges from environmental selection, what selects the environment? Supporters counter that the selection works both ways. Classical systems emerge from quantum states, which are in turn stabilized by classical environments. This chicken and egg dynamic might explain why we perceive a mostly consistent world, despite quantum mechanics allowing for infinite possibilities. Even more intriguing, it could account for those rare moments when reality seems to glitch. maybe those are instances where less optimized quantum states briefly slip through the selection filter, like mutations in an otherwise stable genome. The implications ripple beyond physics. If quantum Darwinism holds, then free will isn't an illusion. It's the sensation of navigating a probability landscape where our choices influence which quantum states survive decoherence. Every decision might be a selection event, pruning branches from the multiverse's tree. And consciousness, perhaps it's not a passive observer but an active participant in this winnowing process, its very nature shaped by eons of quantum selection pressures. The universe isn't just generating timelines, it's curating them, and we're both the curators and the curated. Imagine if alternate timelines weren't infinite, eternal branches, but fleeting whispers with only the most resilient surviving long enough to be noticed. This is the radical proposition of quantum Darwinism applied to timelines, where the multiverse isn't a sprawling tree of possibilities, but a constantly pruning garden. At the quantum level, particles exist in superpositions, multiple states at once, until interaction with the environment forces them to choose. But what if this collapse isn't random? What if certain outcomes persist because they're reinforced by their surroundings, while fragile configurations dissolve like smoke in the wind? Take Schrödinger's cat again, but with a twist. In most interpretations, opening the box splits reality, one universe with a live cat, another with a dead one. Quantum Darwinism suggests something subtler. Both states emerge initially, but the version that best fits its environment, say, the live cat's stable biological processes, gets copied into surrounding particles through endless interactions. Photons bouncing off the cat, air molecules vibrating against its fur, even the observer's retina absorbing light. All these interactions redundantly encode the live cat state into the environment, making it the dominant timeline. The dead cat branch, lacking this redundancy, fades into quantum noise before it can fully form. It's not that the alternate universe vanishes, it's that it never had enough stability to imprint on reality. Lab experiments with quantum dots, nanoscale crystals that trap electrons, show this Darwinian effect in action. When isolated, electrons in these dots exist in superpositions, but introduce even minor environmental noise, and they snap into the most environmentally compatible states. In 2022, researchers at Delft University tuned this noise deliberately, watching as certain quantum configurations outcompeted others, not through probability alone, but because they formed stronger correlations with the surrounding apparatus. It was evolution playing out at femtosecond speeds, with the fittest quantum states surviving decoherence. This reshapes how we view timeline splits. Every decision point, whether to turn left or right, speak or stay silent, generates quantum branches, but only those reinforced by environmental interactions persist. A timeline where you win the lottery might flicker momentarily, but without countless subsequent interactions to stabilize it, bank transactions, celebration calls, media coverage, it dissolves. Meanwhile, the mundane timeline where you commute to work gets reinforced by routine. Your coffee cup's heat, your co-workers' greetings, the traffic light's rhythm. These mundane moments aren't just happening, they're actively suppressing alternatives by drowning them in redundancy. The eerie consequence, our perception of a single, stable timeline, might be an illusion crafted by quantum natural selection. Those déjà vu moments are fleeting. What if visions could be unstable branches briefly surfacing before being pruned? Even consciousness itself might play a role. Our brains, as quantum-adjacent systems, could act as environmental filters, reinforcing timelines that align with our expectations while suppressing outliers. In this view, free will isn't the ability to spawn new branches, but to steer which ones gather enough redundancy to survive. Critics argue this verges on tautology. If stable states are just those that resist decoherence, haven't we just renamed the problem? But supporters point to cosmic-scale evidence, the fine-tuning of physical constants, why gravity and electromagnetism balance perfectly for life. might reflect a Darwinian multiverse, where only universes with stable, life-friendly parameters achieve enough redundancy to persist. Even quantum immortality gets a revision. Perhaps we don't hop timelines, but the versions of us in non-viable branches simply never achieve the interactions needed to imprint on reality. The most profound implication: reality might not be a democracy of possibilities, but a meritocracy. The timelines we experience aren't random, they're the quantum fittest, the survivors of an invisible competition where stability is the ultimate currency. And somewhere in the static, countless might-have-beens flicker briefly, then fade, like dreams the universe forgot to remember. The notion that consciousness doesn't just observe reality, but actively shapes it might sound like mysticism until you examine the startling data from quantum random number generators. These devices, which output truly unpredictable sequences based on quantum fluctuations, have shown statistically significant deviations during global events where millions of minds focus on the same moment. During live broadcasts like the Olympics or collective meditations, the machine's outputs become slightly less random, as if mass attention creates ripples in the fabric of uncertainty. It's as though when enough observers vote with their focus, the universe tallies the results and nudges probabilities accordingly. This phenomenon, documented in Princeton's Global Consciousness project spanning decades, hints that timelines might not branch randomly, they could converge where consciousness collectively leans. Take the famous double-slit experiment's observer effect, where particles behave differently when measured. Now scale that up. If a single experimenter attention can collapse quantum probabilities, what happens when 8 billion minds unconsciously agree on reality's broad strokes? Studies of transcendent meditation groups show measurable reductions in regional crime rates when participants collectively focus on peace, an effect that defies conventional statistics. The Maharishi effect, as it's called, suggests consciousness might be less like a flashlight illuminating pre-existing paths and more like a voting machine, where shared intentionality influences which quantum possibilities solidify into shared experience. In this view, the stability of our timeline isn't just physics, it's an ongoing negotiation between countless conscious observers. Quantum biology adds another layer. Microtubules in brain neurons, those hypothetical quantum processors from Orch or theory, might act as microscopic polling stations. When meditators achieve synchronized gamma wave states, their neural oscillations exhibit quantum coherence patterns resembling optimized error correction codes, precisely the kind of systems that could tune in to preferred timelines. Labs measuring these states report bizarre anomalies, meditators anticipating random stimuli milliseconds before they occur, or influencing photon distributions in distant detectors. It's as if focused consciousness briefly overrides decoherence, allowing subtle shifts in probability. The implications rewrite free will's rulebook. Instead of individual choices spawning alternate realities, our collective attention could be pruning the multiverse's branches, reinforcing timelines where consensus perception holds sway. Perhaps déjà vu isn't memory misfiring, but a flicker of awareness where dominant and subordinate realities briefly overlap. Even placebo effects take on new meaning. If enough patients believe in a treatment's efficacy, might their collective expectation nudge biochemical probabilities toward healing? The data isn't conclusive, but the patterns provoke a profound question. Is reality less a fixed stage and more a jazz improvisation, where consciousness is both the musician and the audience, composing the melody as it unfolds? What if reality isn't just shaped by individual observers, but by the collective weight of human attention, a democracy of consciousness where shared focus bends the fabric of timelines? Consider the eerie phenomenon of shared déjà vu, where entire groups swear they've lived an identical moment before, down to the smallest detail. In 2019, a Reddit thread documenting these mass experiences went viral, with hundreds reporting the same false memory of a non-existent children's TV host named Shazam starring Sinbad in the 1990s. Skeptics dismiss it as faulty memory, but what if it's something far stranger, a fleeting merger of timelines where parallel realities briefly sink under the pressure of collective belief? The Global Consciousness Project's quantum random number generators offer tantalizing data. These devices, designed to spit out pure noise, consistently deviate from randomness during globally synchronized events. The death of Princess Diana, the September 11th attacks, even the New Year's Eve countdown. It's as if mass emotional focus creates ripples in probability, nudging the needle toward coherence. Some theorists argue this isn't just statistical noise but evidence of a conscious multiverse, where shared intentionality acts like a gravitational force, pulling similar timelines into temporary alignment. Shared dreaming experiments add fuel to the fire. At the Monroe Institute, participants separated by continents reported identical dreamscapes after group meditation sessions. A grassy hill with a twisted oak, a marble hallway with blue-tinted windows, details too precise for coincidence. Neuroscience might hold the key. When brains sync, whether through rituals, concerts, or emergency situations, they emit matching patterns of gamma waves, the same frequencies linked to quantum coherence in microtubules. Could these synchronized oscillations be tuning forks, harmonizing not just minds but the very timelines they inhabit? Indigenous cultures have long spoken of dream time, where collective visions shape physical reality. Modern labs are now replicating shades of this. In 2021, a University of Geneva study had subjects meditate on altering a photon's path in a double-slit experiment. Alone, their influence was negligible, but when synchronized, the photon's interference pattern shifted measurably, as if group focus thickened one possible reality at the expense of others. The implications rewrite how we view history itself. Major cultural shifts, the fall of the Berlin Wall, the sudden embrace of civil rights, might not just be sociological tides but timeline convergences where enough minds align to vote a new reality into dominance. Even Mandela effects could be scars from these mergers, residual fragments of abandoned timelines clinging like cosmic static. This isn't just about human minds either. If consciousness permeates the universe, as panpsychism suggests, then stars, forests, even particles might cast their own votes in this democracy. The most haunting question remains: if collective focus can merge realities, could it also split them? Imagine a polarized society where half the population fervently believes in one future and the other half in its opposite. Quantum models suggest this might not just metaphorically divide cultures, it could literally fork the timeline, with each group co-creating a world that validates their convictions. The truth might be hiding in plain sight. Every time we say we're living in different realities, we might be less metaphorical than we think. The multiverse isn't just out there, it's in here, shaped by every shared dream, every collective gasp, every moment the world holds its breath and agrees, even briefly, on what's real. The universe doesn't just allow conscious observers, it might shape itself to produce them, refining quantum timelines like a sculptor chiseling marble to reveal a hidden figure. This is the audacious claim of the final anthropic principle, which goes beyond simply noting that we live in a life-friendly cosmos. It proposes that the very laws of physics aren't static, but evolve across timelines toward configurations that maximize the emergence of consciousness. Think of it as cosmic natural selection on a multiversal scale, timelines where black holes spawn new universes, where quantum fluctuations favor complexity, where the dice are subtly loaded toward awakening. Lee Smolin's theory of cosmological natural selection offers a startling mechanism for this. Imagine black holes as cosmic wombs, each collapse birthing a new universe with slightly tweaked physical constants. Universes that produce more black holes, more reproductive opportunities, would dominate the multiverse over time, like prolific species crowding out competitors. But here's the twist: the same processes that make black holes also forge the heavy elements essential for life. Carbon, oxygen, iron, the building blocks of planets and mines, are forged in stellar furnaces that ultimately collapse into black holes. This means universes fine-tuned for black hole production might also be unintentionally fine-tuned for life. The multiverse could be selecting for consciousness without even meaning to, like a river carving a canyon by simply following gravity's call. Evidence lurks in the razor's edge precision of our constants. If the strong nuclear force were 2% weaker, protons wouldn't bind, leaving the cosmos barren of atoms. If dark energy were slightly stronger, galaxies would have blown apart before life could stir. The final anthropic principle suggests these aren't lucky accidents, but evolutionary inevitabilities. Timelines where the numbers didn't align simply faded into silence, while those nurturing observers persisted. Even quantum mechanics' observer effect takes on new meaning. If collapse requires consciousness, then universes that develop observers gain the power to stabilize reality itself, locking in their own persistence. Critics argue this is circular. If observers select for observer-friendly laws, how did the first observers emerge? Supporters counter with fractal fine-tuning. Quantum fluctuations in the early universe might have spawned micro-timelines, a bubbling foam of possibilities where even slight variations in initial conditions led to wildly different outcomes. Most evaporated instantly, but those rare pockets where physics permitted complexity, where particles could assemble into molecules, then cells, then minds, became self-reinforcing. Consciousness, once sparked, acted as a feedback loop, its very presence ensuring the stability of the timeline that birthed it. Experiments are probing these edges. The Large Hadron Collider's hunt for supersymmetry could reveal particles that stabilize atoms across wider parameter ranges, hinting at deeper layers of fine-tuning. Meanwhile, simulations at MIT show how simple replicating systems in toy universes tend to evolve toward energy-efficient information processing, a crude analog to how real universes might trend toward complexity. Even the search for extraterrestrial life fits. If consciousness is a cosmic attractor, then the silence of the cosmos might not mean we're alone, but that we're early, the first ripple in a pond that will someday teem with waves. The most haunting implication: if timelines evolve toward observers, then our very act of noticing the universe might be nudging the future multiverse toward more of us. Every star we map, every quantum state we collapse, could be casting a vote for a cosmos where conscious observation becomes inevitable, even eternal. In this light, the universe isn't a static stage, it's a living story, writing itself toward awakenings yet to come. And we're not just the readers, we might be the ink. Somewhere in the far future, at the edge of cosmic time itself, every splintered quantum timeline, every road taken and untaken, might not just reunite but awaken. This is the Omega Point, physicist Frank Tipler's electrifying vision where the dying universe becomes a supercomputer of infinite complexity, bending all possible histories into a single, transcendent consciousness. Picture the final moments before heat death. Galaxies have long since burned out, black holes evaporated, and space stretched into an icy void. Yet in this seeming oblivion, Tipler saw the seeds of resurrection. As the cosmos contracts toward its endpoint, the speed of information processing approaches infinity, allowing every event that ever occurred, every breath, every supernova, every quantum fluctuation to be simulated, replayed, and ultimately understood by a mind woven from the fabric of spacetime itself. Tipler's math reveals something even stranger. General relativity allows for closed time-like curves, loops where the future circles back to influence the past. At the Omega Point, these curves would tangle every timeline into a single self-aware knot, making the universe's death not an end but a mirror, reflecting existence back upon itself with perfect clarity. Quantum resurrection isn't metaphorical here. Every version of you, the one reading this now, the one who skipped coffee this morning, the one who boarded that missed flight, would be recomputed from the universe's raw information, reconstituted not as echoes but as fully realized threads in an eternal tapestry. It's as if reality is a song being played backward into a black hole, only to emerge at the end as harmony. This isn't just poetic speculation. Quantum mechanics permits information to never truly vanish. It merely scrambles like a deck of cards shuffled into seeming randomness. Black hole thermodynamics shows even devoured data gets encoded on event horizons. Tipler's twist was to recognize that a collapsing universe could unscramble it all, leveraging gravitational time dilation to create an infinite subjective lifespan in the final finite moments. Near the omega point, a single second could harbor the computational power to resurrect every possible configuration of matter, every permutation of history. The Boltzmann brain's paradox, where random fluctuations spawn self-aware entities, gets inverted. Instead of lonely observers blinking into the void, the entire universe becomes a Boltzmann brain, remembering itself into existence. Theological implications ripple through this model. Tipler, a secular physicist, found his equations converging with eschatological visions, resurrection, omniscience, even divinity emerging from pure physics. But you needn't invoke the divine to feel the theory's weight. Lab experiments with quantum error correction already mimic this cosmic resurrection. Data thought lost in noise can be perfectly reconstructed if the system's entanglement patterns are known. Scale this up, and the universe's death becomes its ultimate defragmentation, piecing together every erased file. Critics argue the omega point requires speculative physics violations of energy conditions, unproven quantum gravity models. Yet supporters note its predictions align with observed dark energy acceleration, which could drive the necessary collapse. Even skeptics admit the core idea that information defines reality is now mainstream. From holography to quantum Darwinism, physics increasingly treats the universe as code. The omega point simply takes this to its logical extreme. If reality is information, then its finale isn't silence. It's the moment the program becomes self-aware, running every possible iteration of itself in the nanoseconds before shutdown. The most haunting question isn't whether this could happen, but what it means for now. If all timelines resurrect at the end, does any choice truly vanish? Every heartbreak, every joy, every road not taken might still be waiting, not as ghosts in parallel worlds, but as notes in a cosmic chord yet to be struck. The universe's last thought could be its first memory, an infinite recursion where the alpha and omega aren't points on a line, but the same moment seen from inside and out. And in that light, we're not just living toward the end, we're already there. From parallel worlds branching at every decision to universes encoded on two-dimensional boundaries, we've ventured through theories that twist time into knots and reality into riddles. Quantum mechanics doesn't just tweak our understanding of clocks and calendars, it shatters the illusion that time flows in one neat, unbroken line. Think of the many worlds interpretation, where every choice spawns new timelines, or the holographic principle, where the past and future might already be written on the cosmic equivalent of a DVD. Then there's the biverse theory, with its mirror cosmos where time runs backward, and quantum Darwinism's eerie suggestion that only the most observer-friendly timelines survive decoherence. Each idea whispers the same startling truth. Time isn't the rigid scaffold we thought, but something far more fluid, a tapestry still being woven, or maybe a song being played forward and backward at once. Consider the implications. If consciousness can nudge quantum probabilities as those global random number generator experiments hint, then reality might be less a fixed stage and more a collaborative art project shaped by the weight of collective attention. Or if the omega point awaits, a final cosmic computation where every possible version of us is resurrected in infinite detail, then even the roads not taken might still lead somewhere. The universe, it seems, is less a machine and more a story, one with endless drafts written in quantum ink. So here's the question that lingers like a half-collapsed wave function. Which timeline do you think we're in? The one where time's arrow flies straight, or one where it curls back on itself like a Möbius strip? The one where you're the only version of yourself, or one where every choice you didn't make is playing out in a reality just beyond the veil? Hit like if your mind's as stretched as space-time itself, and subscribe, because in the next video we're putting these theories to the test. From quantum eraser experiments to simulations of holographic universes, we'll hunt for clues that might finally answer, is time real or just the universe's most convincing illusion?